Okay, friends, time for lesson 8, which kind of closes up our look at applied optimization. Truth be told, applied optimization used to be a much bigger part of AP Calculus than it is right now. The College Board got tired of people missing questions because of geometry and not because of calculus, and so there really is not a whole lot of applied optimization anymore. But I would like to work through a couple more classic problems with you. If you didn't get to the end of the last video, you really want to, particularly because our project is based entirely on that, but also because that's a classic problem, surface area volume. Today I want to do a couple, so it's a short video. If you're prepping in the textbook, then, well, it's still short. So here we go. We already did that. We already did that. We already did that. We are not doing that. Let's try this. Here's a question for you. How close does y equals radical 4 minus x squared come to the point 42? This is a standard classic question. How close does the graph of y equals radical 4 minus x squared, and we know that that is a half circle, how close does that graph come to this point right here? We imagine that it's this distance here. I mean, we imagine that, but I don't know how to figure that out unless I have some expression for distance. So let's remind ourselves, based on everything we've done so far, what it is that we are about to do. We are about to come up with a function that defines the distance between 4, 2 and a point on the curve. And then we are going to take the derivative of that function so that we can analyze its derivative and notice, okay, d is increasing on this interval, decreasing on that interval, and then we'll be able to see, using a first derivative test, when this function is at a max. So here's my thought. Distance is the square root of x2 minus x1 squared plus y2 minus y1 squared. This is a generic point xy, so x2 minus x1 squared, y2 minus y1 squared. I don't want to use y. I want to have one variable. So is there anything in the world that's equal to y but doesn't have y in it? Yes. Yes, there is. And so we're going to make that substitution right here. This function, d, gives us the distance between the point on the semicircle and our blue point 4, 2. Now, taking a derivative of a big radical, that's a problem. And so instead, we are going to minimize d squared, because to minimize d squared will minimize d. I want to minimize d squared, and d squared is, so let's call that some big function. Let's call that our f of x. F of x is x minus 4 squared plus radical 4 minus x squared minus 2 squared. Then what do I want to do? I want to take a derivative. I want to set it equal to 0, see where my critical points are. So f prime of x is 2 times x minus 4 plus 2 times radical 4 minus x squared minus 2 times the derivative of the inside. And that's 1/2 4 minus x squared to the negative 1/2 times negative 2x. That's your chain rule. So what does that give me? That's 2 times x minus 4 plus, wow, that is ugly. That is daggone ugly. It's a minus. It's a minus 2x times radical 4 minus x squared minus 2 over radical 4 minus x squared. And so I ask myself, what happens now? Well, if you're really good at algebra, then you crank that out. And if you're not, you say, hey, I want to see what this looks like. 2x times, parentheses, radical 4 minus x squared minus 2. 2x times, parentheses work, divided by, ooh, yes, 1, 2, 3 opens, 1, 2, 3 closes, divided by radical 4 minus x squared. We're checking at home. What's our window? Our window is going to run from negative 2 to 2, even though we're pretty sure it really only should run from 0 to 2. And the distances aren't that big. So let's see. Yep. And we're going to find a root. Itsy bitsy spider. Common. So what have I got? I've got a root at x equals 1.789. Here's my number line. My number line runs from negative 2 to 2 because clearly x cannot be outside of negative 2 to 2. F prime appears to be negative before 1.789 and positive after 1.789, which means that not only is x equals 1.789 and a local min, it is the absolute min. It's not only a local min because f prime changes from negative to positive, it is an absolute min because there's never another place where that function turns around. So I know that the graph, the red graph, comes as close as it can to the blue point at x equals 1.789, and the only question is, what is that distance? So I want to figure out what that distance is. So I take the square root of parentheses 1.789 minus 4 squared plus parentheses square root of 4 minus 1.789 squared minus 2 squared. And sure enough, the minimum distance is 2.472. And it occurs when x equals 1.789. Again, the rhythm. The problem leads to a picture. The picture shows us a formula. The formula leads to a derivative. The derivative leads to critical points. The critical points tell me maxes and mins. I'm going to go one more. In this particular case, I've got a farmer. Oh, that is a terrible rectangle. I've got a farmer, and the farmer is going to build a corral. And the farmer is going to build the corral with 500 meters of fencing. And it's going to be a rectangle on the bottom and a semicircle on the top. Rectangle on the bottom, semicircle on the top. 500 meters of fencing. What I want to do is I want to maximize the area of the corral. That's what I want to do. So the problem leads to a picture. That's my picture. How do I start putting variables in there? Well, what am I going to need? I'm going to need the radius of that semicircle, that's for sure. And so I know that the width of my rectangle is going to be 2r. Then what is the length? Well, I don't know. I've got 500 meters of fencing. So if I've got 500 meters of fencing, that's got to cover the width at the bottom plus the circumference of a semicircle, which is pi r, plus 2 lengths of the rectangle, which means that 2 lengths of the area, 2 lengths of the rectangle is 500 minus pi plus 2 r's. So each length is 500 minus pi plus 2 r's over 2. I hope that makes sense. I hope that makes sense. So I want an area function. I want the area of the corral. And the area of the corral is half the area of a circle plus the area of the rectangle. And the area of the rectangle is 2r times the length of the rectangle. And surely we can clean that up just a bit so that this is pi over 2r squared plus 500r minus pi plus 2r squared. And that can be cleaned up so that it's 500r, and then how many r squareds do we have? Oh, how many r squareds do we have? Well, we have pi over 2 minus pi minus 2. That's negative pi over 2 minus 2 r squareds. That is the area function. I know at a critical point, the area function's derivative is 0. So A prime is 500 plus 2 times negative pi over 2 minus 2. Oh, really? I went all magic pen, did I? So sorry. So very sorry. Let's try that again. 500 plus 2 times negative pi over 2 minus 2r. So I want that to be equal to 0. I want 500 plus, let's do this right, negative pi minus 4r to be equal to 0. Which means I want 500 to be equal to pi plus 4 r's, which means I want r to be 500 over pi plus 4, and that will be the critical point for my area function. What is, whatever my interval is, r is going to have to be positive. This is an A prime chart. R is going to have to be positive, and it can't, I imagine, be any more than 250. Because if r is 250, then I just have flatness. So this spot right here is the only critical point on the interval. Now, you and I both know that this A prime is going to go positive, negative, 0 there. And so I know that the area function is increasing until 500 over pi plus 4, and it's decreasing after 500 over pi plus 4. And so that means that not only is r equals 500 over pi plus 4 a local max, it is the absolute max. There cannot be a higher point on the area function. Cannot be. So what do? We say that the area is maximized when the radius of the semicircle is 500 over pi plus 4. That's what we say. Okay? Okay. Wonderful. That's good enough. Good enough. All these problems have the same rhythm. You're going to check critical points. You're going to check endpoints. You're going to make sure you've got it. And that's going to do it. Okay. Well, thank you. All right. Yes. Tomorrow.